So our first speaker is Zebene Girma from Addis Ababa University in Ethiopia. And they'll be talking about 3 GDPs with 3 groups and block size 5. So take it away.
Thank you. Thank you so much. Thank you, the organizers, for giving me the chance to present our research work on this symposium. My name is Zebene, as you mentioned earlier. I am currently a PhD student at Addis Ababa University, Ethiopia, currently working with Professor Sarbat from College of Charleston, USA, on areas of GDDs and T designs. So this is one of our current work, which is actually still ongoing, but ready to be submitted for publication. So here are the outlines of my presentation. Can you hear me? Sorry.
We can hear.
Okay, thank you. So here are the outlines of my presentation. I will try to say a few things about just those basic things, then as introduction, then I will skip to the necessary conditions for the existence of those kinds of designs. Then we will see some elementary constructions, and at the end, we will see some specific GDDs when N is 3. That means when we have groups of size just 3. So this is again, this is part of combinatorial design, which is mainly about whether it is possible to arrange elements of a finite set into subsets so that certain balance properties are satisfied. So the fundamental question in general in just combinatorial design is existence questions. So both group divisible designs, which I use here as GDDs, and T designs have been studied so far, and they provide actually a challenging area in the construction of combinatorial designs. Sarbat, Professor Sarbat from College of Charleston, USA, has combined group divisible designs and T designs to define S3 GDD. This new definition has actually the potential to raise many more generalizations and challenging existence problems. So what is a combinatorial design? Combinatorial design is a pair XB such that X is a set of elements where B is a collection of blocks, which collection of blocks, non-empty subsets of X. A balanced incomplete block design is another basic types of combinatorial designs, which is mainly denoted by this one, BIBD VK lambda, or this one, where B is the number of elements in some given set B. B is the number of blocks in a design. R is, we call it the replication number, the number of blocks in which every element occurs. K is the size of each block, or the number of just subsets of the given set B, and lambda is the number of blocks in which every 2 elements of B occurs. So in order to be this design exists, there is a necessary condition which must be satisfied, but the converse may not be true. So lambda into B minus 1 must be the same as R times K minus 1, and B times R must be the same as B times K for the design to exist. A group divisible design is another combinatorial design, which is actually a collection of K element subsets called blocks of M times N set B. Here we have M groups of size N each. So in general, we have a set B of M times N set, a collection of blocks of size K. Lambda 1 is actually the number of blocks in which every 2 elements from the same group occurs. We call them the first associate pairs. Lambda 2 counts the number of blocks in which every 2 elements from different blocks occurs, which are called the second associate pairs. So here we have some elementary examples of BIBD. If we have a set B of 6 elements, and if we have a collection of blocks which are formed by 3 elements from this set V, then in this design, we have actually like 10 blocks of size 3 each, and every 2 elements from this set occurs in exactly 2 blocks. Simple example of group divisible design. We have 2 groups of size 4 each, and the size of each block is 4 here. Every 2 elements from the same group, for instance, if we have 2 groups, G1 and G2 of size 4 each, every 2 elements from the same group, like 1 and the 4, occurs in exactly 2 blocks, and every 2 elements from different groups, like 1 and the A, occurs in exactly 3 blocks. A T design is again another type of combinatorial design, which can be defined as a pair XB, where X is a set of V elements and B is a collection of K subsets of X called blocks, such that every T subset of X occurs in exactly lambda blocks. So we call lambda here the index of the design. For group divisible designs with 2 groups and block size K, the concepts of GDDs and T designs are generalized as follows. Professor Sarvat, with his colleague Bazire, has defined a 3 GDD for 2 groups of size n each, block size K, number of first associated pairs, number of second, lambda 1 here counts the number of blocks containing every triple of type just 30 when all the 3 elements are from the same group. Lambda 2 counts every 3 subset where 2 elements are from one group and 1 element is from the other group. This is just a kind of mixer type, 2-1 type. So for instance, if we have this GDD, this design exists. So here we have 2 groups of size 3 each. So we have a set X of 6 elements, which is a union of the 2 groups. And the blocks of this design are given by this one. So every 2 subsets from, every 2 elements from the same group, it can be from G1 or from G2, occurs in exactly, here we count as the number of triples in each design. So every 3 subset of type 30 occurs in 3 blocks. For instance, all the 3 elements of this design, 1, 2, 3, occurs in 3 blocks. The same is true for this one, and every 3 subset of type 2-1, mixed type from 2 groups, occurs in exactly 1 block. So here, for instance, if we have 1, 2, and A, then 1, 2, and A occurs exactly in 1 block of just this design. So this definition has been extended by Sarvat and Trube to include more than 2 groups. So before we go to that definition, let's define first a 3 partially balanced incomplete block design, which is denoted by this one. This is defined as just a design where every 3 subsets from the same group occurs in exactly θ1 blocks. Every 3 subset of type 2-1 from 2 groups occurs in exactly θ2 blocks, and every 3 subsets from different groups occurs in exactly θ3 blocks. So Sarvat and Trube has defined a 3 GDD for just where the number of groups in a design is actually greater than 2 as follows. So it is a pair XB, where X is a set of M times N elements, and B is a collection of K subsets of this set X, such that every 3 subsets occurs exactly μ1 times if it contains at most elements from 2 groups. That means every 3 subsets can be chosen from the same group or from 2 groups. So triple of type 30, when all the 3 elements are from one group or from the same group, or triple of type 2-1, where 2 elements are from one group and 1 element from the other group, occurs in exactly μ1 times, and every 3 elements or every triple of type like 1, 1, 1, when all the 3 elements are chosen from different groups, occurs in exactly μ2 blocks. So they defined this. So this definition is actually the subject matter of my presentation, and we explicitly consider here when the number of groups is actually 3 and the size of the block is 5, and we denote such GDD by just this one. So M is 3, K is 5. When me1 and me2 are equal, then this design is just exactly a 3. It becomes a T design when T is 3 with just a set with 3 n elements. So we have 3 groups of size n each. So in total, we have 3 times n elements of block size 5, and every 3 subset of this set, the set with 3 times n elements, occurs in exactly me1 blocks, and the existence of this design guarantees the existence of this one, or vice versa. So as now, the next section of my presentation is about just, so based on this definition and taking M is equal to 3 groups and block size 5, and assuming that this design exists, we try to derive just the results, which will help us to find the replication number, the number of blocks containing some given first associated pair, and the number of groups containing some given second associated pair. So in this design, the replication number can be calculated by using this result and the number of blocks in a design. If this design exists, then surely RB lambda 1 and lambda 2 must be integers, since they count those things in a given design. Then the replication number is given by this one, the number of blocks is given by this one, the number of blocks containing some given first associated pairs, 2 elements from the same group becomes this one, and 2 elements from different groups occurs in exactly lambda 2 blocks. So from this theorem, we can just derive or generate some results as corollaries. So S3GDD, this one does not exist if mu1 is not multiple of 3. If mu1 is not equivalent to 0 mod 3, then this design does not exist. We can easily just see this one from these results, since 3 divides this one, and in order to be lambda 1 is an integer, 3 has to divide mu1. Otherwise, this lambda 1 cannot be an integer, hence the design will not cannot exist. So if this design exists, then this one must be different from it has to be different from, I mean, it has to be multiple of 3. Otherwise, the design does not exist. Similarly, since the number of groups is less than the block size, and since me1 counts the number of blocks in which every triple of type 30 or 21 occurs, and me1 cannot be 0, the same is true for lambda 1. Another result, we have given this design, mu2, this is the number of blocks in which every triple of type 111 occurs, and is less than, must be less than 3 times me1, and the number of blocks in a design must be greater than or equal to this result. I mean this. The other result is just when n is less than or equal to 5, when the number of elements in each group is less than or equal to 5, then this design does not exist. And actually, we have proved that this design does not exist when n is less than or equal to 5, and actually here when mu2 is 0. If our design does not contain triple of type 111, when 3 elements from different groups are not there, then such design does not exist. If we have a design, if all blocks of a design are of type 32, that means the size of the block is actually 5. So if all the blocks are of this form, 3 elements from one group and 2 elements from the other group, then these 3 partially balanced incomplete block design exists, and the number of blocks in that design is given by 6 times n choose 3 times n choose 2. When the number of blocks in a design are only
Yeah,
of type
about 5 minutes left.
Okay, thank you. Are when the number of blocks in a design is of type 50, then this design exists. And substituting here, for instance, when n is 6, this one and this one are equal. So as a result, we have S3 GDD with mu2 is equal to 0. And the other thing is just when a design, when all blocks are of type 41, such design does not exist. And for n greater than or equal to 6, then we have already proved that this design always exists. This design always exists. So we have some examples by substituting here some specific values of n, like 6, 7, and so on. Similarly, if n is not equivalent to 2 mod 3 and n is greater than or equal to 6, then S3 GDD with mu2 is equal to 0 and mu1 is equal to this one exists. So there are some examples which are a sequence case of that one. The other point is just the last section of my presentation is when n is 3. When n is 3, those 3 partially balanced incomplete block designs just exist, and those designs actually help us to just construct the blocks of those 3 GDDs. So when P is less than or equal to Q, then we can, using those previously mentioned examples of 3 balanced, partially balanced incomplete block designs, it's possible to show that those designs exist. And for P less than or equal to Q, we have this design. The existence of this design can also be proved. So similarly, we can just prove that when P is greater than or equal to 1, this 3 design with actually mu is equal to 30 times P exists, and for P greater than or equal to 0, we have actually this design. So since this is actually an ongoing work and the proofs are not included here, and I hope you understand me that, and here we have used those materials for our work. Thank you so much. Thank you.
Okay. You can use the clap react to thank the speaker. Okay, so are there any questions? You can either raise your hand and unmute or ask a question in chat and I can relay it. I might ask one first then.
Okay.
So can you explain some of the motivation behind studying these 3 GDDs in particular? So what are they usually used for?
Actually, designs are mainly used in areas of, for instance, like coding theory and just chemical synthesis. Sometimes, you may have, for instance, different substances, and you may want to just determine the number of even all those possible options you have to just put one substance with the other, satisfying some balanced property, certain balanced property. And actually, this may be sometimes too much, and people nowadays use robotics to combine one element of one set with just another element of another set. And we may want to just completely determine the number of all those possible options which we have before just by using actually those calculations. So the first thing is we need to know whether such kinds of arrangements is actually possible or not. So we have to just deal with the likes of actually those necessary conditions and then all those preconditions which must be met to construct those kinds of designs. It's actually helpful in areas of statistics, in areas of actually like coding theory, where you code just different things, and in areas of chemical synthesis. So the pattern has to be known. And mathematicians has to actually sit down, I think, first and determine all those things on the paper before we use other maybe sophisticated tools like robotics to combine one element with just other elements.
That's very cool. Thank you.
Thank you so much.
Stacy has a question.
I think, yeah.
Yeah,
Someone
hi. Sorry. Is there a reason you considered 3 groups in blocks of size 5, or is that kind of just something that hadn't been done yet, or is there like a particular reason that you kind of focused on that case?
Yeah, you know, this is a recently defined problem. Previously, just people were working either on GDDs or T designs. Now, as I mentioned in my presentation, Professor Sarvat combined those two things, T designs, 23, and group divisible designs, 3 GDDs. So this is something which is recently defined, and that's why we are working on that.
Makes sense. Thanks.
Okay, thank you.
Are there any more questions? Oh, Jeremy has one.
Okay, Jamie.
Hey, this is just a small question. Out of all the results that you've given, which one is your favorite, I guess? Which one do you think is the most interesting to you?
You know, here we have those results, for instance. Just let me go back just in it, and as part of elementary constructions, for instance, just this result. Can you see my slide?
Yeah.
You know, to get this one, the proof involves some pattern construction, and I really even though I like all of those results I mentioned here, and I think this one is something which you sometimes, you know, get it even when getting it is slightly challenging, and I think this one is one of those interesting results.
Yes. All right. Thank you.
What did you say? Sorry.
I just said thank you.
Thank you so much. Thank you.
Are there any more questions? We might have time for a short one. If not, we can thank the speaker again.